Imagine drinking satellite imagery from a fire hose. You are thirsty, but you can't manage to drink it all. And even your multi-terabyte mass storage systems fill up far too quickly. You need to delete old images to make way for the latest up-to-date imagery that the fire hose will deliver tomorrow and the day after and the day after. But what if deleting old imagery leaves you with blind spots on the globe? Murphy's Law says those blind spots will be critical to mission planning the second you delete them. My name is Paul Brewer, and I'm Director of Image Analytics with DZYNE Technologies Incorporated. And today I have the opportunity to tell you about a SBIR program called Cloud Analytics of Satellite Imagery for Tomahawk mission planning that applies advanced deep learning technologies to tame the imagery fire hose and optimize global satellite imagery assets to give Tomahawk missile mission planners the reference images that they need when they need them. DZYNE Technologies just celebrated its 10-year anniversary. In a single decade, we have grown from a 3-person startup to a 175-person company with employees based in 15 states and 80,000 square feet of facility footprint that house our R&D, prototyping, manufacturing, and software engineering organizations. Our autonomy and analytics software group, which I manage, develops advanced full-motion video, satellite analytics, and autonomy solutions that are the brains of our aircraft, as well as other systems in the DoD and intelligence community. DZYNE's mission is simple: create innovative, intelligent, autonomous aircraft. We have developed aircraft that range from the small Group 1 hand-launch and tube-launchable fixed-wing aircraft to heavy-lift multirotors that operate in autonomous counter-UAS applications, to the large. We have achieved over 37,000 combat hours on our Group 4 and Group 5 long-endurance fixed-wing ISR aircraft. Our LEAP aircraft has greater than 30 hours of endurance and is a fully autonomous system that is 5 times lower in cost than the MQ-1C Gray Eagle and achieves in excess of 7,000 hours of operation between failure. The original topic associated with this effort is titled Software Analytics Exploiting Commercial Satellite Imagery, and the objective is to develop more sophisticated imagery storage management capability for intelligence, surveillance, and reconnaissance, and remote sensing systems than currently exist, with focus on deep learning-based, content-aware management of imagery from various platforms, while also expanding capability to address still frame imagery from tactical sources. In short, the Navy is on the receiving end of a fire hose of satellite image assets and limited ability to retain those assets for use in mission planning activities. Current image exploitation systems that are directly connected to the fire hose quickly fill their available storage and either fail or begin dumping imagery using some very simplistic management scheme. This scheme is typically a first in, first out approach. Just delete old images. The quality of the imagery thus held at any point represents the result of this default image dumping strategy than it does the intended needs and mission success of the system operator. I refer to this as a you get what you get and don't get upset approach to image asset management. Under a related program called Psychos, we exploit image metadata to recommend image assets for deletion or retention. Under CASI, we seek to understand the image content to retain the best quality and most relevant imagery that will enable mission success. During this phased program, we will work towards processing up to 80 terabytes of imagery on a daily basis in order to optimize the mission planning imagery asset library. By way of an example, suppose the current image library in a certain region consists of 814 high-resolution satellite images. Some areas may have many images looking at the same place in the globe, while other areas may have no coverage in the current library. The bottom images in this slide show that applying a FIFO or first in, first out deletion strategy to image management results in large regions being completely unrepresented in the image library, which leaves the mission planner blind. In past work under the CYCOS program, the user applies a series of rules which lets the system declutter the library of redundant imagery and maintain optimal image coverage. In this past work, CYCOS enabled the user to create and evolve image retention strategies based on image metadata to meet the critical operational need. The CYCOS dashboard provides data retention statistics at a glance, and advanced analytics provide insight into the effectiveness of the image retention strategy that the user has created with the CYCOS tools. When it is in use, CYCOS recommends image sets for deletion and lets the user make the final decision to delete or to iterate on the retention strategy. While our earlier work focused on exploiting image metadata to implement a retention strategy, CASI's focus is to provide content-aware analytics that mimic the workflow of an expert human. CASI's algorithms label the globe in feature space and create 2D vector graphic overlays of buildings, foliage, important surface materials such as airfield tarmac, road networks, water regions, and vehicles. In addition, we create 3D building and foliage models from single-shot nadir satellite imagery. Our 3D algorithms create fast, cost-effective 3D models that provide information about building heights and roof types. Content-aware image analytics help the mission planner to retain critical images while placing lower priority on imagery that are generally not useful to the Tomahawk mission planning process and workflow. We've applied CASI analytics in other domains to monitor and baseline large swaths of the globe in disaster response applications, as well as to baseline key sites such as airfields to characterize construction activity over time. Monitoring the globe to characterize change over time reduces the burden on expert humans to squint at two monitors in an attempt to determine the stability of a given area. Scene stability is important to the process, as regions that change over time are not suitable as optical navigation landmarks. Construction, deforestation, and seasonal changes can be marked and those regions deprioritized in the image library. During phase one, we developed a software prototype that demonstrated image ranking by image content-based rule set and processed and managed 5,000 unclassified images that weighed in at 3 terabytes of storage. During phase two, we will deploy a more mature version of CASI to the Washington Planning Center, where we will demonstrate operation on a classified image set. We provide tools to enable the end user to create, evaluate, and evolve image persistence strategies, and have evolved a software framework to handle additional imagery sources such as PixDB. We managed to get our software installed and tested on site in spite of COVID-related headwinds that limit our access to WPC for large chunks of time. We have signed a technology transition agreement and are moving down a transition path. CASI and CYCOS work together as an even more powerful toolkit. So instead of retaining or discarding imagery solely based on image metadata, CASI uses advanced AI ML capabilities to assess the image itself. Does the image have excessive cloud cover? Delete it. Does the image contain buildings and roads that are mission relevant? Retain it. As I discussed earlier, the baseline image retention approach that we have to beat is a FIFO strategy. Just delete old images. We have demonstrated that we can process 150,000 images, that is 50 terabytes of imagery, in just 5 minutes, rapidly declutter duplicative imagery, prioritize imagery based on a rule set that is iteratively developed by the user, and can clear out the image archive by 2/3 to accommodate the latest up-to-date imagery that the fire hose will provide tomorrow and the next day and the next day. It is a bit of a Sisyphean task, and now CYCOS provides the user advanced AI tools to push that rock back up the hill and focus on faster and more robust mission planning without worrying about the grunt work of managing the image library. Faster mission planning means greater lethality for our users. And our content-aware CASI algorithms better mimic the process and workflow of the expert human image analyst. CASI labels a globe as roads, buildings, and other key features, monitors the globe over time to ensure scene stability in a way that is far more robust than legacy pixel change algorithms. CASI mimics the human and aids the analyst to perform the tedious parts of the job and free up cognitive load to focus on faster planning and greater lethality. We are pursuing a transition to fleet model via integration into the Tomahawk mission planning workflow and have identified additional transition potential in the Tomahawk planning organizations in other branches and with partner countries. In addition, the Psychos image management capability is relevant to many other DoD and intelligence community, as well as industry applications that require the use of significant archives of satellite imagery assets. We are pursuing a transition to fleet model via integration into the Tomahawk mission planning workflow and have identified additional transition potential in the Tomahawk planning organizations in other branches and with partner countries. In addition, the Psychos image management capability is relevant to many other DoD and intelligence community, as well as industry applications that require the use of significant archives of satellite imagery assets. In summary, Psychos and CASI software scan big data satellite imagery archives daily to enable users to move past the current FIFO deletion strategy and implement optimal AI-based strategies that will give them the imagery they need when they need it, and let the user focus on mission planning instead of image deletion. We are well on our way through verification and validation and integration into the Tomahawk Mission Planning Center software framework. Commercial applications include satellite image management and analytics for satellite constellation providers, as well as end users in the land survey, housing, and risk management markets. Thank you for your attention. Please feel free to contact me at pbrewer@dezyntech.com to further discuss the capability and any use cases or requirements you may have. You can also see more of DZYNE's innovative, intelligent, autonomous aircraft at www.dezyntech.com.